All right, so today we're going to be looking at a process called calorimetry. So last time we used the specific heat equation to figure out either the heat gained or lost by a substance if we knew the specific heat, or if we didn't know the specific heat and we measured the amount of heat gained or lost by it, we could calculate the specific heat using Q equals MC delta T. So calorimetry, let's say that we have an unknown metal. In this case, we're going to say our metal, block of metal right here, mass of 50 grams, a 50 gram sample. We place it in boiling water. So we're going to get fancy here. So we're going to say that this hot water, okay, 100-degree water, we know if we boil water, should boil at 100 degrees Celsius, plus or minus 1 or 2 degrees Celsius. We let it sit in there long enough so that the metal block, is just as warm as the water around it. What we do then is we then also have a beaker or a cup full of a known mass of water. So in this case, our water has a mass of 100 grams. We have 100 milliliters of water in there. And luckily with water, 1 milliliter has a mass of 1 gram. And we're going to say it's going to start off at room temp or 23 degrees Celsius. We know water has a specific heat. Let's do that. Water has a specific heat of 4.184 joules per gram. We're going to pretend that's degrees Celsius. Oh, that's not bad actually. All right. The specific heat of our unknown block of metal here, we don't know. So what we can do though is we can place our metal cube, once it's nice and boiling hot, so 100 degrees Celsius, we can remove it from the tub it's in, the beaker it's in, and we can place it in the 100 grams of room temp water. What we should find happen, oh, that's horrible, that's okay though, is once the two are together, their final temperatures should be the same. They start at different temps. In this case, the block of metal started at 100 degrees Celsius. The water started at 23. But we're going to say that their final temperatures will be the same. The metal will cool down and the water will warm up until their temperatures equalize, in which case neither of their, one's not heating or cooling the other. Their temperatures are equal. Thermal energy flows back and forth evenly. So let's say in this case, I want to go back to the white though. There we go. So let's say final temperature of all of this, 37 degrees Celsius. All right, here's where the calorimetry calculations actually come into play. So I'm going to switch to the blue because we know the specific heat of the water. We know the starting and final temps of the water, and we know the mass of the water. So I can actually figure out the heat energy gained by the water. Now, the thing about the heat energy gained by the water, it could only have come from one source, the block of metal. Because the heat, let's see if I can get fancy again. The heat flowed from the metal into the water until they were the same. All right, so let's go there. Okay. So now, our Q. Oh, nope, that's not what I wanted. There we go. Something like that. I'll fix it later. All right. Q of the water is going to be equal to the mass of the water, 100 grams, times the specific heat of water, 4.184 joules per gram degrees Celsius, times the change in temp of the water. Water started at 23 degrees Celsius, ended at 37 degrees Celsius. So do some math here. 37 minus 23. Change in temp, 14 degrees Celsius. Remember, it's final minus initial. All right. Get out my calculator quick here. Where am I going? Huh. There we go. Oh. Okay. Maybe I can't exit. There we go. That's it. All right. So 100 grams of water times its specific heat of 4.184 times change temp 14. That water gaining just 14 degrees, 5,800, make sure I'm double checking, 57.6. And that was heat energy, so joules. So that's the amount gained by the water. So that means the amount of energy, let's go over here, and there. All right. So this number here, the amount of thermal energy gained by the water, we're going to scroll down a little bit here. That's the amount of heat energy lost by the metal block. And so if we're losing it, it's actually going to have a negative value. All right. Scroll up a little bit. We know the mass of the block was 50 grams. It started at 100 degrees Celsius, ended at 37. So the change in temp of the block is 37 minus 100. I'm going to guess negative 63. Let's double check just to make sure. 37 minus 100. Negative 63. Good deal. All right. Change in temp of the block, negative 63 degrees Celsius. Looking at it this way, the only thing I'm missing for the block is a specific heat, which is what I want to calculate. So now I can set it up. Negative 5,857.6 joules equals mass of the block, 50 grams, times specific heat, which is what I'm looking for, times change in temp, which we said was negative 63 degrees Celsius. All right, so just how we would solve just for specific heat, we're just going to divide by the mass times our change in temp. All right, two things in the bottom, so I'm going to have to make sure to put those in parentheses or brackets. Because really, we put 50 grams times negative 63 degrees Celsius there. Cancel, 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 cancel. All right. So our specific heat is equal to, yeah, let's see if I can figure out negatives here. All right. Took me long enough to figure that part out. All right. 5,857.6, and that's negative, divided by parentheses 50 times 63, but it's negative, closing parentheses, equals 1.86, I think is what we're going to round that to. All right. So the specific heat for aluminum block is not aluminum, sorry, just metal block, 1.86 joules per gram degrees Celsius. All right. Calorimetry helps us find the specific heats of unknown metals, masses, solids. Sometimes that will allow us to compare it to a list of known specific heats so we can actually figure out just what the material is. Sometimes if we're working with a new alloy, working with a new ionic compound, stuff like that, this just helps us to understand more physical properties for it. The big thing about this, calorimetry simply involves using that specific heat equation twice. Once to figure out the heat gained by the water, which equals the heat energy lost by the metal, and then doing it again to find the specific heat of our unknown substance. You just got to do it twice. The Q's will be equal. The final temps will be equal between the two substances. Clear as mud, but I'm hoping it helps. Just keep at it. This is really what our lab's going to be about. So with that, good luck.